In this work, we propose the central distance keypoint detector for color point clouds. The motivation is that even though color point clouds can be easily obtained, there's no effective keypoint detectors to make use of both geometry and color modalities, and we believe that incorporating color information in keypoint detection can benefit the downstream systems that are built on top of it. For example, in a typical feature-based point cloud registration pipeline, the feature description is highly dependent on where the keypoints are extracted. To fill in the gap, we propose the central distance keypoint detector that can extract both geometry salient and color salient keypoints in the color point cloud. The overview of the algorithm is the following. For each input point cloud, we will apply the centroid distance saliency measure in both 3D space and RGB color space, and the two measures will be combined by a multimodal non-maximal suppression algorithm to produce keypoints. To apply this measure in 3D space, let's see an example. Suppose that we have a point cloud segment like this, and we are evaluating a point at a corner. We first search within the radius to find all its neighbor points, and then compute the centroid by averaging all the geometric components of the neighbor points. Then the central distance is computed as the L2 distance between the query point and the central point. The higher this measure, the more salient the key point is. We can also see that in case of a flat surface, the central distance is nearly zero. To apply in color space, we can take a candidate key point together with its neighbor points and plot their color components in the RGB color space. Similarly, the central point can be computed by averaging the color components of all points in the neighborhood. Then the central distance is computed as the L1 distance between the query point and the centroid in the color space. Again, the higher this measure, the more salient the key point is. In case of uniform color, this distance is nearly zero. The saliency measures in two spaces are then combined by this non-maximum suppression algorithm. It has two steps. First, we filter out points with low saliency measure in both two spaces. Then we select points with higher response over the contour, which is the multiplication of the two measures. The intuition is that in practice, most points have high response in only one of the modalities. You can imagine points located on the edge with uniform color and points located at flat surfaces with rich color variations. For evaluation and results, let us begin with the qualitative evaluation. This is an arbitrary frame in the point cloud dataset captured by an RGBD camera in the real-world environment. We can see that SAT can capture color changes between floor tiles and extract key points with high regularity, and only SAT, SAT3D, and ISS can extract geometry salient key points on 4 stove knobs. We evaluate the performance of all methods on 4 standard datasets with and without noise added. The result shows that our proposed SAT and SAT3D detectors can achieve the highest repeatability across all datasets. In terms of computational efficiency, SAT and SAT3D can keep running time to a minimum. They are faster than all methods except for the random keypoint selector and the USIP detector, which is a learning-based method that requires additional GPUs. We also compare it against other methods in the task of point cloud registration, which is one of the potential applications of the proposed method. Results indicate that our proposed SAT keypoint detector outperforms others in all evaluated sequences. Thank you for your attention.